Hello and welcome to my presentation today titled Fill Pack to Cool Your Plastic Parts Virtually. My name is Sashi Sitambaram and I'm the simulation person here at CADimensions. So I wanted to start off my presentation today with the question of who is this for? Who is this webinar for, or who can benefit from the product that we're going to show you today? Well, anyone that's designing plastic parts, building molds for plastic parts, or anyone involved in plastic part production that has anything to do with injection molding will find value in today's presentation. You will get some return into this presentation. So, industrial designers, part designers, mechanical engineers, mold designers, all these types of roles will get some return on this time you're spending on this webinar today. So, the known results. Well, a lot of times when you watch a webinar, it's summarized with what the software or what the product can give you. In this case, I actually wanted to start it off by showing you what SolidWorks Plastics, is what I'm going to be showing you today, gives you. What are some of the benefits you get? So predict and avoid injection molding, manufacturing defects, eliminate costly mold rework, improve part quality, and of course decrease time to market. Now this is well known, and I think SolidWorks is notoriously known for putting out software that is easy to use. It instantly decreases time to market. But for today's webinar, the question is how do we get these results? It's known that it can do all this, but how do we get to that point? I think that is the most important aspect, and I think you as a future user will be able to see the value in it. Now the how is highly driven by the results. What type of results you can get from SolidWorks Plastics. And when I mean results, not saying decrease time to market, improve part quality. What I mean is actual results. How will my part fill? Is there any air traps? Is there any weld lines, knit lines? Is there any voids? Those are the types of results I'm talking about. And these results are highly driven by inputs, your inputs into the software. Now this is important because there's really two spectrums to this. One is the users who want to automate everything, who says, I put my part in, run the analysis, I want to see what's going on. And then you have the other spectrum where a user says, I want to be able to put in every parameter that I would put in when I run this injection molding process into the analysis. And you can do that both sides. We cater to both sides. So if you want to automate the process, we can. If you want to have full control of every input, we can as well. So the theme of today's webinar would be what inputs you can put in and what are some of the results you can get from those inputs. All right. So just a quick agenda. We're going to start with what the database is, basically what SolidWorks Plastics has to offer globally, and then we're going to look at filling the mold or the cavity perhaps, and then we would move into packing the mold. Once we've packed the mold, we're going to start cooling and check for warpage analysis, and then we're going to end this webinar today with cooling analysis, essentially running cooling lines through your mold to see how it cools the part down. So we'll start off with database and filling the mold. So SolidWorks Plastics database, what does it have to offer? Well, for one, SolidWorks comes with more than 5,000 polymer in its database. So this comes with every version of SolidWorks Plastics. So it's not where when you buy one version or you buy the next version, we unlocked more polymers. That's not the case at all. So you get all the polymers that's available right off the bat. 187 mold materials, which also translates to your insert materials. So if you have any type of inserts into your mold, you can also use the mold material database or the polymer database. And last but not least, 39 types of coolant that you can use for your cooling analysis. Injection molding machine data. So we have a huge list of most of the injection molding machines that are out there today, and you can actually either get information from it or input information just to cross-reference. So it doesn't really impact the analysis, but it ensures that you're using the right values. Results advisor, where it advises you on some of the results you get. And getting started wizard, which is very helpful for new users, as some of you might be in the near future, and I'll show you how that will help tremendously. So let's hop into SolidWorks real quick, take a look at some of this mentioned databases. So for one, we have the polymer. So within the polymer, as I had mentioned, over 5,000 polymer materials right here. It can be sorted by family. So you can see your ABS, your PP, your EPDM, it's all here. Or you can also sort by company. So you can see all the big players are here: 3M, Asahi, DuPont. They're all here. Honeywell, they're all here. All right. So obviously, looking through 5,000 materials might be a little bit tedious. We actually do have a find tool here. So if you select on this find tool, you can type in something like a code or a number, and it will give you a list with that number that you put in, or whatever words that you put in, the keywords that you put in. All right. The next thing is the mold database. As you can see, I mentioned 187. So all the aluminum alloys, steel, copper alloys, iron, and if there's even some other obscure material that you might be using as a mold, you can even define it on your own. So you can see here we have a user-defined database right here. As long as you have all the right values for your specific heat, thermal conductivity, density, you'll be able to plug that in yourself. Again, the find tool is right here, so you don't have to really scrummage to 187 materials. You can find it right from here. The next thing that we have is the result advisor. So when we take a look at some of our results, anytime you select on any of the different type of results that we have, now I'll be going into this a little bit deeper to the webinar, you can actually select on an advisor right here, and it shows you, or it talks about that specific result that you selected on. So in this case, this part can be successfully filled with an injection pressure of 65.6 MPa. And it talks a little bit about what the average temperature at the end of the fill means to this simulation. So fill time, it gives you some information in terms of fill time, and even gives you some recommendation on gate locations and how to reposition the gate location to better fill your product. So very helpful for even new users, not to SolidWorks simulation, but even new users to injection molding. The last thing that I wanted to show you in terms of the database is the getting started wizard right here. So this getting started wizard allows you to select on it, and it basically walks you through the first step, the first phase, which is the filling phase. So as soon as you hit next, you can see that I've already met all the 6 steps here, and when you run this, it basically go through each step with you and advise you on how to apply the right materials and how to put in your process parameters. In this case, it will be your fill settings. it might be your injection location or your filling time, or the injection pressure limit in this case. Then you can run the analysis and get the results. So before wrapping up this part of the analysis, there's one more thing that I actually wanted to show you, which was the machine database. So again, all the big players are here. As you can see, all the different manufacturers, and as you select on these, you can actually take a look at some of their information in here. So injection unit, what the injection pressure limit is, and what the clamping force is here, your heater wattage. So quite a bit of information in here. You don't have to go and really look for them. They're all in here. They all have been verified to be correct. In any case, if it's different from what you have, you can always notify SolidWorks, or you can even change it yourself. Okay, so the next part of this presentation is going to be the filling process. So before we jump into that, I just wanted to kind of give you a quick overview of the injection molding cycle. Now, most of you here probably know this cycle by heart. Now, I wanted to show you this because I wanted to relate this to the software, what the software has to offer. Well, in terms of SolidWorks Plastics, you're able to run a simulation from A to A. This is all that we cover. So filling the analysis, packing it, so basically the holding phase where it's packing and cooling down. If there's a co-injection, we are able to do that. So co-injection switch point by using some valves. Once we've packed it, we can run a warpage analysis from how it cools down and even how it falls out of the mold. And of course, during the cooling process, we can even run a cooling analysis based on our cooling lines and the type of coolant we are using. So, as I mentioned earlier today, earlier to this presentation was the theme of this presentation is going to be input data and results. So, filling the mold, what are some of the input data that you can apply in your analysis? Well, obviously the first one is the polymer type. So the polymer type we've already seen, again 5,000 plus. The next thing is your filling time, your melt temperature, mold temperature, injection pressure limit, and injection location, so gate location. So again, a lot of this can be automated, as I'll show you, or you can even apply it based on some of your criteria. So from a result standpoint, what can you get if you input these types of data? Well, for one, did it fill? You'll answer that question. Or will you experience some sort of short shots where it didn't fill? In that case, you can always change the geometry, maybe add added pressure, or if the walls were too thin, you can evaluate that within SolidWorks Plastics. You can check for air traps, where you can find voids. You can look at the knit lines or the weld lines within your part based on how it filled, and also of course sink marks. Sometimes you might have ribs in your analysis in your plastic parts, and those can cause sink marks in your part. So let's hop into SolidWorks and take a look at some of this. So in terms of the input data, you would go into your fill settings right here, and as I had mentioned, fill some of the parameters that you can put in, such as filling time, melt temperature, mold temperature, and injection pressure limit. If you uncheck the auto right here, you can put this number in. So for instance, if you have a criteria where you need to have the part filled within half, maybe point half seconds, you can apply that. Because you might have a criteria of a requirement of putting out 10,000 parts a day or 100,000 parts a day. So you obviously have a time criteria there, and you can fill that in. and you can check and see what needs to be changed in the part to be able to meet that filling time. Obviously, you can also hit the auto, and SolidWorks will recommend an amount of time to fill that in. And this is based off the geometry that you have, the material that you set, and also the polymer, or the polymer that you set, and your injection location. So once you've set all that parameter, that's really all you need for a filling phase, and then we can take a look at some of our results. So the first thing when it comes to your filling is you want to see how it fills up part. So if you just hit the play button, you can actually see how it fills up. And if you take actually a closer look, you can actually slow this down, and you can see and try to identify if there was any voids in this system. And I actually did see one real quick. So let's go ahead and put this in. Look at that right there. That is what's going to cause a void. So this phenomenon is typically called race tracking, where the way the material is flowing, it combines or it joins at this area right here, which causes a void. And what would the result of this would typically be an air traps. So if we max this out and select on air traps right here, you'll be able to see that right away. So an air trap somewhere at the end of your part here is not too bad. Typically you can bend this out using some pins, but in this analysis, having an air trap right there in the middle of the part might not be very good. So you might have to change some of your geometry to remove that. Besides air traps, obviously you can also take a look at some of your well lines. So in this case, all the well lines show up. Again, this is based on the flow of the material. So by changing some of your geometry, changing your gate location, changing the pressure, you might be able to remove or reduce some of the well lines that are available. So let's take a look at how we can quickly remove this air trap right here. So using SolidWorks as a platform, you'll be able to quickly change geometry. So in this case, I was able to just go into my configuration, select another geometry that I have here with the thinner material, go into my results, and if you take a look here at how the material flows now, it actually flows much better. And when I select for air traps, it actually removed that air trap from right there. So again, having that benefit of a 3D modeler as your platform through this analysis allows you to quickly change your geometry, rerun your analysis to identify issues in your model early on, in your design phase, as we would call it. All right, so other than some of the issues that we just saw, such as air traps and well lines, sink marks can also be a big issue. So let's take a look at minimizing your sink marks. So here I have a part with a fairly large rib here. So if you take a look at the results and I select sink marks, you can see how it actually generates on the other side. Very visible. So to be able to visualize this physically, or think about some of the cheap plastic parts you've seen, you know, maybe like a toolbox, a cheap toolbox. Usually you will see some white scuffs on the outside where the ribs would be on the inside. This is typically what we call as sink marks. So by again using SolidWorks to maybe make these ribs a little bit thinner, so I have actually a better part here. you can see that the ribs are actually much thinner in this case, and if you take a look at the analysis results, the sink mark has significantly reduced, and it looks a lot more pleasant, so not giving a very unpleasant white scuff type of look. Alright, so the next thing we're going to look at is some advanced filling options that we have here. So the first thing we'll take a look at is creating some multiple cavities, and when you have multiple cavities, typically you need to have a runner, and how do we create those runners? So those are some of the input data, and based on that input data, what are some of the results that we can take a look at? Obviously, injection balancing, runner balancing, and insets to your insets temperature. Switch back to SolidWorks. So the first thing I will show you is creating multiple cavity. So in this analysis, you see here that I have two parts, which is it's a plastic part. It looks like a remote, and this lines right here is basically what signifies that runner. So again, just using SolidWorks, the basic SolidWorks tools, in this case there's the sketching tool, we were able to just sketch out the profile of the runner, and when you move into SolidWorks, you use the channel design, and to create that runner is basically as easy as selecting that line and applying the diameter, so the starting diameter and the end diameter. So in this case it tapers, so this is like a tapered wall, so you might start with in this case there's 8 and it ends to 6, so it actually starts at 6 and ends at 8. So you can apply that, and when you hit apply, it will create the runner for you, the sprue and the gate. So very easy to use. So this is more of a manual technique to create the runner, and again, just like everything else in SolidWorks, you can also create SolidWorks using an automated technique. So here's an example where we would use what we call the runner wizard, and you can see there's a lot of preset type of runners. So end gate or banana gate. In this case, I'm actually going to select a one-side layout, and all I need to do is just select those 2 points right there, and then just input all your parameters. So in this case, I have 480, 4, 6, 6, 3, 6, 8, 1, and 2. And take a look at that. We already have the runner was created. So we were able to do this by just simply placing 2 points using our sketch tool. It's very easy to do. Okay. So when it comes to creating runners, one problem that you could run into is having an imbalanced runner. So here's an example where we have 2 different parts, so top and a bottom, but it's part of the same mold, and it's going to be part of the same cycle. Well, the problem is the volume might be a little bit different, so the amount of plastic that's going to be shot into this cavity and this cavity has to differ in terms of time and pressure, because of the volume, and we want it to be simultaneously. Well, SolidWorks helps you with that, and we actually have a tool here called runner balancing. And what runner balancing does is it evaluates your volume of your material, of your part, and also the polymer that you're using, and it will actually redistribute the thickness of your existing runner. So you might have set this to maybe 4 and 6 or 8 or something, and the runner balancing will readjust that diameter, and you'll see here even at the gate point, this gate is 2.6 and this gate is 2.8. So this one is a little bit bigger, so there's probably more plastic allowance in here as opposed to this, which gives you that more balanced plastic distribution. Okay, so that covers all our filling type of results. So the next thing I want to show you, for that, let's just recap our some of our pre-processing data after filling. So I know that we looked at the results, but here's a list of all the results that you have. So fill time, volumetric shrinkage, that's a big one, cooling time, sink marks. Just keep in mind that a lot of these results, such as the sink marks and volumetric, is a more conservative type of result. So obviously when you're just talking about filling your part, a lot of this information is interpolated, right? So if you want to get a volumetric shrinkage, typically you have to jump into the holding phase, and then you will be able to get that information. So you will see that when we run our packing analysis and our warpage analysis, we get much better results for our volumetric shrinkage. But again, at a first level, you are able to at least get some direction or some information on what type of volumetric shrinkage you're dealing with, or even sink marks. So the next thing we're going to look at is packing the mold. What kind of input data that comes with packing the mold? Well, pressure, holding time, cooling time, injection pressure, and of course using inserts. Now if we have inserts, how are we going to deal with that, right? Basically overmolding, and so I know that I mentioned inserts temperature earlier. Well, using inserts is part of fill, but because we are running it through the packing analysis, now we can also test to see what the temperature distribution of those inserts are. So you might have some plastics or metal that is being put through some high temperature that's coming from your plastic, and based on that, it could either deform and cause some problems, or it might melt if it's a polymer. So we need to be able to evaluate things like that. Alright, so let's hop back into SolidWorks and take a look at some of my examples here. So I'm going to start with showing you my gate freeze analysis. So here we will run a packing, run the filling and the packing, and let's take a look at some of our pack results, pack settings. Here is the pressure holding time. Again, you can set this to auto, or you can set this by yourself. So in this case, I'm going to set it to 7.5, and then the pure cooling time after it's packed, after it's completely filled, how much time you're going to allow it to cool. Again, you can set that to 7.5. Now, right within the pressure holding, the pack settings, you also have the ability to specify injection pressure during that packing phase. So in this case, I've said basically 0 to 7.5. The injection pressure is 30, and after 7.5, it basically tapers off. Okay, so let's take a look at some of our results here. So you'll see in this example we have two tabs. One is the flow tab and one is the packing tab. So in terms of your packing analysis, you can view your temperature at the end of packing. That's a very important one. And the reason for this is because you want to ensure that we don't have a gate freeze phenomenon. So essentially what a gate freeze is when your gate, the plastic in the gate solidifies before it completely packs the cavity. Now obviously that's going to cause some problems, because once this is solid, the plastic is not going to be able to flow through it anymore, and it's going to cause a huge defect. One way to test for this is to identify what the glass temperature is of that polymer. So we can actually step back for a second, go into the polymer settings, take a look at that temperature right there. So glass transition temperature is 244. If you go back into our pack results, we can set that temperature at the end of the packing. You can set this to 244, and we can take a look at where the plastic is at that temperature. So in this case, the plastic is still flowing, and it's towards the end of that flow. So we're at a pretty good stage right now. So the plastic is still flowing. So this is a fairly good product that we have here. Now let's just say if that glass transition temperature was a little bit higher, let's say 286. Now if you take a look here, you will see that there is a small gap between that gate and the plastic part, and it has solidified. So this would cause a huge problem. Essentially the plastic would stop flowing into the cavity. Other than that, because of this packing, we've run this packing stage, we also get much better results for volumetric shrinkage. So when I select volumetric shrinkage, let's take a look at volumetric between 5 to 10%, and you will see the areas that would basically have shrinkage between 5 to 10%. Now 10% might not be a huge value depending on the size of your part. If it's really big, 10% might not be significant. If it's a small part, sometimes some medical devices, then 10% might be huge, it might be significant. So it really depends on your part and the parameters that you set for this analysis. So one more example that I wanted to show you in the packing phase is the using insets. So here I have a plastic part which has some copper inserts. So this is like a piece of end of an electric cable probably. And if we look at how we've set it up, well, for one, we have the inserts, and I mentioned before the inserts is being run by either the polymer database or the metal database. In this example, I've set the insert to be copper. And you can also apply some insert settings. So what is the initial temperature of your inserts and the mold wall temperature as well. Now this is very important because again, this insert could deform based on those temperatures or the change in temperature, and that could cause your plastic part to have defects. So let's take a look at the flow analysis in this. And let's take a closer look inside of how the plastic flows and flows around those inserts. You can see that here clearly it actually bypasses all those inserts and creates the plastic as predicted. All right. So that wraps up the packing phase that I wanted to show you today. Just a quick overview again, what is the pre-processing data that we can get after packing. One of the big ones was the temperature at the end of the packing to ensure that it's not freezing up, it's not causing any gate freezing. Volumetric shrinkage, that's important as well, and temperature at post-filling end. So you might want to see what temperature it's starting at after the packing phase and how much you need to what type of parameters you need to set to be able to cool it down to its appropriate temperature. So the third section of this presentation is going to be our warpage analysis. So the warpage analysis, the input data essentially is the ambient temperature, because we need to know what the delta T is, where it starts and where it ends. Secondly is the direction the part falls out of the mold. We will be able to input that as well. In terms of results, we get much better volumetric shrinkage. So again, you've seen we have volumetric shrinkage at the filling phase and the packing phase, and now we can even get it from the warpage analysis. Displacement due to warping, of course, right? When you warp, it can either displace it more in the X direction or Y direction, and you need to be able to see that. More accurate sink marks. So again, as I mentioned before, the sink marks we get from the fill analysis is more conservative. This one gives you more realistic results based on the warpage as well. In more residual stresses, which is what is causing the warpage. You'll be able to see all those types where it's the highest stress areas are, and of course the quenching thermal stress. Back into SolidWorks. Warp analysis part. So here's a nice example where I actually have the solid modeled of the runner. So we don't even have to use the runner tools. I actually just have it as a solid. And I just use some of our parameters to identify this as the runner. And I also have an insert here, and this is the plastic part. So if you take a look at our plastic analysis for our warp settings, again we have the ambient temperature and the gravity direction, so the direction in which the part falls out. So here's how the mold would look, right? If the plastic is being shot in here, this is the mold, the front and the end of the mold, and then the plastic would fall in this direction. So that's your X direction right there. So let's take a look at some of our warp results. When you select on the warp results, a little bit different in this case. One is you can actually specify which area of the results you want to look, because we can get a lot of results from warping. So in this case, I'm just going to say read all, so we can take a look at all the different results we have. And so we'll start off by looking at our sink mark profile. So when I select sink mark profile, you can actually see all the sink marks that are present in the part. So there's quite a bit of ribs on the back here, but in terms of displacement, 0.03 millimeters, so it's not that much. We could get away with it, and again, this gives you much better results in comparison to the field analysis portion. The next thing we can take a look at is some of our displacement. So based on the total stress, what kind of displacement is involved. So here we only deformed by 1 to 1. So if you want to take a look at that a little bit closer, we can actually bump that up. So this is by 10 times, and you can actually see, even play that the warpage to see how it's warping. Now you might want to dive in a little bit deeper to see the warpage in a certain direction. So I can even specify X direction and play that, and you can actually see the warpage only in the X direction in this case, which seems to be the most significant one here. So other than that, we have our in-mold residual stresses, we have our quenching thermal stresses, and total stresses in combination of all these, but this is without the fibers. Now, just so you know, as you run these analysis, all these analysis is tied into each other, right? It is the full cycle. So as you run the warping analysis, your flow analysis also gets much better. So what I mean by that is when you select on your flow analysis, you will see that now you have some added results here that come from that warp results, warp analysis. And for instance, I can say velocity vector, reduce the number of vectors here, and you can actually take a look at how the plastic is flowing in terms of vectors. So play now, you can actually see it much clearer. This is also the case for fiber orientation. Play, you can see how that fills in. Okay, so that wraps up our warpage analysis. The last thing that I wanted to show you, or before that, is I wanted to again just kind of go over some of the results we get pre-processing data from warpage. Of course, all effects of displacement, so X, Y, and Z, the total stress, the in-mode residual stresses, so you can identify high stress areas, and again, a lot of these results will also affect your flow and pack analysis. So the last part of this presentation is going to be our cooling analysis. This is probably the one of the more cooler parts of SolidWorks plastics, no pun intended. And take a look at my example here, cooling analysis. Actually, let's take a look at some of the input data that we can put into our cooling analysis. So in terms of input data, we have our cooling channels. How do we set up those cooling channels? So it's very similar to the runners. Basically, you sketch it in and you specify the diameter, and it creates those cooling channels. You can specify the shape of the cooling channel. So there's three, well known in the industry: general, baffle, or bubbler, where you have two channels within one cylinder. You also have to set up a virtual mold. So a virtual mold essentially is where the cooling channel is running through, and obviously when you have a mold, now you also have to set a mold temperature and the type of coolant that's running through that mold. Besides that, you also have your coolant parameters, right? The flow rate, the temperature, the coolant starting at, and all that stuff. So what type of results that you can get from this input data? Well, one is the cooling time. So very important, we need to know how much time it takes for your part to cool down. Average temperature of part, heat flux, and really to answer the question, how much heat was removed. So it might be too much, might be acceptable. You'll be able to see that. In terms of cooling time, one thing that you can do is you can proceed cooling analysis, run the cooling analysis first, get the cooling time, and then put that cooling time into your warp analysis and see what type of warpage you're getting based on that cooling time. Right. Now here you can see that we are back to our original part at the start of the presentation. And let's take a look at our cooling lines here. So I actually have an example where I don't have the cooling line set yet. We'll go through that real quickly. So for cooling line, all you need to do is set up the mesh. You'll say the runner and cooling system design. You also want to select the virtual mold generation. You can actually see the sketch that I put in beforehand. And right away it will bring you into this channel design, and again just specify the diameter. In this case the diameter is all consistent, it's all 10. You hit next here. This is the virtual mold. So instead of using a coordinate from that point right there, you can also just specify the size of it. I say add, and that's it. You have your cavity, you have your mold, sorry, your cooling channel, and then you have your mold. All right. So let's take a look at some of our results that we have here for our cooling channel. Or before that, let's just jump into the settings first. So once we've set the cooling channel, you'll be able to set the coolant. So as before I mentioned, we have 39 types of coolant. So you have all your coolant 25, your Dow Frost, your Dow Therm. It's all here. Water, oil. In terms of your cooling settings, you can set your inlet melt temperature, coolant temperature, air temperature, mold open time, average coolant flow rate. So all this you can get from previous analysis. So you can run a flow and pack analysis, get that information, plug it in here, run this analysis, and then run a warpage analysis as well. You actually can run each analysis before each other to get this to get the right cooling settings. So other than that, you also have your cool pipe. So here, your cool pipe settings, you can specify how the temperature is going in and out of your system. So in this case, you can see that I have my cold water going on the top, and then my cold water going in from the bottom here. So I have my cooling coming from both sides. All right, so once we have all that set up, we can take a look at our results. So obviously the most important criteria here is your cooling time, right? As I mentioned before, if you take that cooling time, you can now plug that back into your packing phase to evaluate what type of parameters you might change there, or get some results from the warping analysis. Again, this you're also able to run through this min and max to see which areas are being affected by in that time period. Other than that, we also have our cycle average temperature. So again, what are some of the temperatures we are dealing with here as we are cooling the part? And of course your cycle average heat flux. So in this case, joules per second, meters square second. And again, using that min and max, you'll be able to identify this a little bit more in depth. Now the last question that you need to answer is how much heat you've actually removed from this analysis. Well, we actually do have a text file here that gives you that right away. So if you open that text file, cool text, you'll see as you scroll to the bottom, you have actually all the results right here in numbers, and the top most result, heat removed from cooling channel, equals 7485 joules. So that might be too much, might be too little, or might be acceptable. So you'll be able to design your better cooling system based on this, which in turn then will give you better warpage results. All right, so that kind of wraps up what I wanted to show you within SolidWorks today. So here is a list of pre-processing data that we can get in cooling. So part cooling time, cycle average temperature, it's all here. Before I wrap this up, I just wanted to show you what's available within the different levels of SolidWorks. So Plastic Standard, Plastic Professional will give you access to some of the shrinkage, shrink mark analysis, insert overmold, and then once you step into warping and cooling, you'll get the Plastic Premium. So I've covered most of these modules today. So one of the modules that I didn't get to show you is the valve gate. So this is where you are able to control which gate removes plastic. First, you can see this gate opened up and then this gate opened up. Other than that, we also have some fiber analysis by fringence. You can also evaluate some cooling time here. You can take a look at nodal temperature. So this is very, very useful again, as I had mentioned before, with your inserts. You'll be able to look at graphs at how much of a spike a temperature your inserts are experiencing. You also again insert overmolding. So here's an example of a toothbrush, and you're only filling in that area of the plastic. All right, so SolidWorks plastic. So again, the known results: extensive database, comprehensive range of analysis, guided analysis setup, easy and accurate to learn, easy to learn and fast and accurate. Now, just so you all know that SolidWorks Plastics has been around for a few years now, but SolidWorks Plastics is actually spawned from Simple, and Simple has been around for many, many years and has been used in the plastics industry successfully many times over in many large companies. So the solvers that we are using in SolidWorks Plastics is all from Simple, so the results is very much reliable. And of course, the SolidWorks integration, being able to use the 3D model as your basic platform, you'll be able to model your parts and run your analysis simultaneously to design better parts early on in your design cycle process. And again, there cannot be any other plastic analysis tool that ties in as well with SolidWorks because of the integration. When SolidWorks as a new version, there'll also be a new version of SolidWorks Plastic with added capabilities. The CADimensions Commitment. Well, let's talk. If you saw anything today that in this webinar that you find useful, give us a call and we can talk about it further. Even come and visit us if you feel like you want to take a spin in the software. Feel free to come in for an hour, half an hour, 45 minutes, whatever time commitment you have. Come in and we'll go over some examples. We'll let you run it and see how easy it is and how realistic it is to use. On-site meeting, we are more than happy to come on site to your facility, learn about your applications a little bit closer, better understand your application, so that we can recommend the best version of plastics for you. We are not really out to sell you the biggest, most expensive software. We want to fit you with the right solution. That's really what we do here, is providing you with the solution that you need, and of course training. All plastics, everything that you saw today is part of our training program. So you will be able to run all the type of analysis and get all the results that you saw today based off the training that we provide with the software. So here's my contact information. If you want to know more, please email me at sashi@CADimensions.com. You can call us at 877-223-4255. So it's just about 1 o'clock now, so right on time. So thank you, and I'll open up the floor to any questions right now. All right, so no questions at the moment, but if you do think of one, please, again, here's my contact information. Send me an email, give us a call, and we'll be more than happy to answer them. Thank you, and have a great day.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.